Hello everyone. Today we're gonna work through this problem of fluid mechanics. Let's read the problem statement first. Consider the U-tube manometer shown in the following figures. The reservoirs and tubes have circular cross sections and the fluids are incompressible. Part A, in the left-hand figure for the free surfaces of both tanks are exposed to the atmosphere. Determine the value for H. Uh, B, in the right-hand figure, the free surface of the right-hand tank is exposed to gauge pressure delta P. If the fluid interface in the tube moves downwards a distance as delta H equals 0.2 meters, what is the change in the elevations of the left and right-hand tanks? That is what are delta L and delta R. C. Determine delta P in the right-hand figure when delta H is equal to 0.2 meters. So this is a multi-step problem. Um, but let's first break it down. So in our previous video, we described what a manometer is. And so in the left-hand figure, the free surfaces of both tanks are exposed to the atmosphere, and we want to determine the value for H. So for part A, we will perform a manometer analysis on the system in the left figure. So let's go ahead and do that. So before we jump into this problem, we have to know what gamma 1 and gamma 2 means. And those are usually symbols for specific gravity. And what is specific gravity, you might ask? Let's go and look at a definition. In short, it is rho, the density, multiplied by gravity. Here's a formula sheet that summarizes what gamma means. So actually, I was wrong. It was specific weight. So gamma is equal to rho times gravity. Specific gravity is the one that is rho over um the density of water at 4 degrees Celsius. So be sure not to confuse specific gravity and specific weight. But basically, specific weight is a shorthand form of writing the density of a substance multiplied by gravity. Let's go back to our problem now. So we know that the specific weight of fluid 1 is gamma 1, and the specific weight of fluid 2 is gamma 2. Um, and what we know in a manometer is that points at equal elevations represent points of equal pressure. So these 2 points, for instance, at the same elevation from the bottom are at the same pressure. We can use this to our advantage because this means that the hydrostatic pressure at this location minus this hydrostatic pressure at this location should be equal to 0. So how can we express that? Um, we know that hydrostatic pressure has the general form rho g times the change in height or h. But over here, the rho g is represented as gamma, either 1 or 2. So over here, it is gamma times change in height, or height. So this means that gamma 2 times the height, which is r plus h, to this point, must equal gamma 2 times L plus H. Because those 2 points are at the same pressure, and pressure is equal to this. So those 2 points are the same pressure, so they must be equal. Now you might ask, what about atmospheric pressure? Atmospheric pressure is the same on both sides, so they basically cancel out on both sides. But if you want to be explicit, you could have added atmospheric pressure on both sides. But they will just cancel out. And also, if we were considering atmospheric pressure, we will be considering absolute pressure. But here, if we are only considering these two pressures from these two fluids, another way of looking at it is that we are considering gauge pressure. So the pressure relative to atmospheric pressure, not the absolute pressure. So what we wanted to solve for is the value for H. So we have two equations over here, and we can rearrange it to solve for H. Basically, gamma 2 times R plus H minus gamma, oh, oops, sorry. This one is actually gamma 1. I don't know if you guys caught that, but this one is supposed to be gamma, oh wait, no, this one is gamma 2. This one is supposed to be gamma 1. Yeah, so gamma 2 gamma 2 times R plus H minus gamma 1 times L plus H is equal to 0. We can now isolate H because we can factor out H times gamma 2 minus gamma 1 uh plus gamma 2 AR minus gamma 1 L is equal to 0. So thus H is equal to gamma 1 times L minus gamma 2 times R all over gamma 2 minus gamma 1. Now we can plug in the values we need. And let's see what those let's see what those values are. So we can plug in our values for gamma 1 and L. So gamma 1 is 2000 Newton per over meters cubed. L is 0.5 meters. And then gamma 2 is 1000 Newton meter cubed. R is 1.5 meters. And then we put it over gamma 2, which is 1000, and then we minus 2000. And then all this is in terms of newtons over meters cubed. So the height should be in terms of meters. So if it checks out, we should have meters in our last dimension after doing unit analysis. So let's calculate this out to be 0.5 meters. And that is our value for H. Okay, now let's move on to part B. Yes, so let's continue with part B now. Um, they, this is conservation of volume, basically for part B. And the free surface of the right-hand tank is exposed to gauge pressure delta P. If the fluid interface in the tube moves downwards, a distance of delta H equals 0.2 meters, what is the change in elevations of the left and right hand tanks? That is what is delta L and delta R. And those two values are the values over here. So delta L and delta R. Um, so basically, we note that the fluid volumes remain constant. So the right-hand surface is exposed to gauge pressure delta P, which means that the pressure there will be probably uh larger. Since it doesn't say that the gauge pressure is negative, and it also says that the fluid interface in the tube moves downwards a distance of h equals 0.2 meters. So that is delta H. So this means that the gauge pressure is indeed be because of a pressure that is higher than the atmospheric pressure. So if this side moves downwards, this side must move upwards. So we already know that the delta L is going to be positive and delta R is going to be negative, since delta R is going to be from this fluid moving downwards, and thus is going to be a negative change if we define our coordinate axes as x being positive and y being positive upwards. Because moving downwards means that the final position is lower than the initial position. So that is why the change is going to be negative. And yes, and all of this is in terms of delta H. We know that because of volume conservation, uh, when this fluid moves down, the the fluid from this volume, because as you push this fluid down, the fluid too is going to increase in volume over here. However, fluid 1 is going to move upwards a certain volume. And these volumes, the volume that fluid 2 moves down is actually equal to the volume that fluid 1 moves upwards. It's just that the heights are different, since uh D is greater than the small d over here, which is the cross-sectional area of the thin tube of part of the manometer. So we can equate these two volumes, and we want to ask ourselves first, what is the change in volume associated with fluid 2 as you push it down like this, and it is equal to the change in height multiplied by the cross-sectional area, which is um, pi small d squared over 4. And since fluid 1 is going to move up, we want to ask ourselves, what is the volume change associated with that increase in height? And the answer is that it is delta L, which is the change in height, multiplied by big D squared over 4. So we will write those down. So since the fluid volumes remain constant, what is true is that we have delta L d over 2 squared times pi, because pi r squared is the general form for the cross-sectional area. But over here, big D is our diameter, and big D over 2 will give us our radius. So over here, this is essentially r squared times pi, which is pi r squared. So we have height times area, which gives us a volume. Just so that you guys understand how this works. And then we set it equal to change in height is equal to small d over 2 squared times pi. And this one is the volume change associated with fluid 2. Now there are certain things that cancel out on both sides, which is nice. The two terms also cancel out, so we're left with delta L times d squared is equal to delta H times small d squared. Now we can find an expression for delta L in terms of delta H, small d, and big D. Basically, delta L is equal to delta H times D squared over big D squared. And we can now plug in our known values. We know that delta H is 0.2 meters. We know that D squared, or D, small d, is 0.1 meters. We know that big D is 1 meter. So we have 0.2 times D squared, which is 0.1 squared, over big D squared, which is 1 meter squared. And this is in turn equal to 2 times 10 to the negative 3 meters, or 0.002 meters. And an interesting thing to note here is that although the change in height over here, delta H, is negative because this whole column of fluid is moving downwards, we don't use a negative 0.2 for H because we're considering delta L on this side. And delta L on this side is going to actually be opposite to the change in height, which is delta H. So if we had used negative 0.2 for delta H, which would be correct because delta H is actually moving downwards, we will have to reverse the sign on our delta L, since delta L happens on the other side and it's going to be positive increase in height instead of a negative decrease in height, because the negative decrease in height here causes a positive increase in height over here on the left side. Yeah. And yes, so now we have delta L, and we want to find delta R. Delta R is going to be similarly, if we think about this in a similar fashion, it's going to just be the negative of delta L. Basically, delta L is equal to negative delta H times D squared over D squared. This is equal to negative 0.002 meters. Because delta R times D squared must be equal to negative delta H times D squared over delta over D squared. And over here we do not use negative 0.2 for delta H. We simply use 0.2 meters for delta H, and then we negate it to get negative 0.2 meters, because it would be confusing if we don't have a consistent if we don't keep a consistent format. But anyway, just know that delta R is negative of delta L, because if delta L is moving upwards a certain distance, this is because of the fluid being pushed down a certain distance on this side. Um, Yes. And basically, now that we have our given information, we can calculate certain quantities like H plus delta H, L plus delta L, and R plus delta R and compare them because we know the values for H, which we found in part A, we know the value for L, and we know the value for R. H plus delta H is going to be 0.5 plus 0.2, which is 0.7 meters. L plus delta L plus delta L is going to be 0.5 plus um 0.002, which is 0.502 meters. And delta and R plus delta R is going to be 1.5 minus 0.002, which is 1.498 meters. So note that these are the total heights if we add the change in heights. Now we want to move on to part C, which is determine the delta P in the right-hand figure when delta H is equal to 0.2 meters, which was the condition we used in part B, our previous problem. And for this, we can examine the system in the right-hand figure and use our hydrostatic pressure analysis again. So basically, this is similar to what we did for part A. Basically, we want to find a point at which the pressures are equal, and a convenient point is this point over here. The pressures at those points are equal to each other, and we'll use this height as H plus delta H. And so basically, yeah, so for part C, we have delta P as a pressure, and it is gauge pressure, which means that it is taking atmospheric pressure to be 0. So we don't have to worry about atmospheric pressure here. Um, because that means that we don't have to add atmospheric pressure on this end as well. We can do that if we're taking it to be absolute pressure, in which case it will be P minus P atmosphere, the atmospheric pressure, but it's unnecessary since atmospheric pressure will cancel on both sides. So we can take the left side pressure to be 0 gauge, mm, and put it relative to the atmospheric pressure as we did for the delta P. So in that case, both of these pressures will be gauge and they will be they'll be considered in the same way. So the pressure at this point over here must be equal to each other. So we first find the hydrostatic pressure at that point for the right end, and then we find the hydrostatic pressure at that point, the same elevation for the left side, and then we set them equal to each other. So for the right-hand side, we have delta P plus um, the specific gravity of fluid 2, which is gamma 2, and we multiply it by the height, which is R plus delta R. And then we add it to the specific gravity of fluid 2 times this height over here, which is h plus delta h. And for the left side, we have that the hydrostatic pressure at this point over here is equal to gamma 1 times L plus L and plus gamma 1 times H plus delta H. So gamma 1 times uh, L plus delta L plus gamma 1 times H plus delta H. So basically, we can solve for delta P. So delta P is equal to gamma 1 L plus delta L plus gamma 1 times H plus delta H minus gamma 2. And I'm just going to combine these two. R plus delta R plus H plus delta H. So computing this and plugging in known values we have. Yeah, so gamma 1 is 2000. So let's plug in known values. So 2000 and L is 0.5. Delta L is 0.002. Okay, and then we're actually gonna add H. So H is 0.2. Or no, H is 0.5. So and minus delta 2 or gamma 2, I mean, which is 1000. Then we're gonna have R plus delta R, which is 1.498. And then plus 0.7. And we're getting the values actually from here. We can get the values from there and then just plug it in actually. It will be easier than plugging in each of these values again. So delta P is this equal to 206 pascals, which matches the answer that we were expecting over here. So I hope this going through this problem was helpful for you guys, and I'll be posting these slides afterwards in the comment section. So thank you guys again so much for watching this video. See you next time.